If I get the right thing on here. All right, so I sent out an email if you missed the test on Friday. Technically, the school, like if you were absent, missed it, that's already passed. I opened it up for one more shot. It closes at 9, and if you did not take care of that by that time, then you are getting a 0 for the test. Let's see here. I did catch in the assignment yesterday, there was a question about the adaptation, the mutation of the gymnosperms. And I originally had that true vascular cell structure was the most important, because honestly, that's what let them go inland. But I had mentioned the seed development as well. So I went back, and if you either answered both of them or the one that, in my opinion, that vasculature was more important, I gave you credit. So if you saw your grade change, it should have only gone up. We sort of talked about that in fifth period. We had some interesting conversations in fifth period about what was going on yesterday. But anyways, today we're talking about what is called continental accretion. Accretion means to build up, okay, to like assemble. That's what that word means. And I should have talked about this. On our entire planet, which is the youngest mountain range? Not mountain range.
What?
Which is the youngest mountain range on our planet? The newest one to have formed.
Overseas.
And it's not in this country.
As of one in Asia.
But it's somewhere over there, yeah.
Is it like one with Mount Everest?
Yeah, which mountain range is the one that has Mount Everest? What are they called? No. You're so close. It's right in that area.
Himalayas.
It's the Himalayas. Okay, the Himalayas are. No, you said the Alps. The French Alps are not in the Alps are young too.
I knew what I was trying to get at.
In general, the taller the mountain chain is, like the higher elevation is, the younger it tends to be. It's newer. There's less time. No. If it's older, it's had more erosion, and erosion tears them down. So in general, now it's not 100% like set in stone that way, but in general, your smaller mountains, like a lot of the chains in Africa and like the Appalachians, because they've had more time to erode, they're not as tall as what they used to be. Parts of the Appalachian Mountains are 1.2 billion years old. Okay, so the Blue Mountain Range, that section of the Appalachians is actually older than the other parts of it. There are two mountain ranges in our country, two major ranges. Which would be the younger in our country?
Smoky Mountains.
No, that's part of the Appalachian system. That's the older system. What's the other major mountain system in the United States? What is it called? Oh, come on now.
I don't know it.
You don't know any major? No.
Colorado.
Okay, Colorado has some of them in it, but that's not the name of the range. What is the name of the entire range? There we go, the Rocky Mountains. Which there are other parts, like the Cascades are part of the Rocky Mountains. Like there's others, like there's like little subsections, depending on the specific time period that they formed. Now, I am going to mention a few of these. Here, what I did with my clicker today, but mountain formation is specifically what we are talking about tomorrow. So the continental accretion is a lead-in to mountain formation. We'll get more in depth with some of them tomorrow. There are different types of mountains. We're not doing that today. Friday, I have us planned to do ice ages, and then we'll specifically talk about glaciers, how they're formed, and what they do to the surface of the earth as they're literally slowly grinding across the rocky part. Because glaciers are destructive, but they have a purpose too. The things that they leave behind can be beneficial, but in general, you don't stop a glacier stops you. Like, you just don't. Like, it moves everything out of its path. All right, so we have been talking about the Wilson cycle. I just didn't call it the Wilson cycle. This is the repetitious cycle that keeps happening with the land mass, whether it be continental or oceanic, the crust of our planet. So, and I know we talked about Pangea yesterday, that Pangea wasn't just always there. It wasn't just boom, it blinked into existence. There are certain parts of our continents that did form first. The older parts, the shield parts that came from archaea, that came from when it was just bacteria that was alive. Okay, but Pangea had the form. So you have, if we're starting from Pangea, because I don't have enough time to go through all the different types of Earths that have existed here. There are things that happened before Pangea. I may be able to get into them later, but right now I don't have the time in this unit. But we have Pangea, we had the Gondwana, and we had Euro-American, and they smooshed together and they made the Appalachians, and then we had other little bits that came from the north, and then we had Caphasia that came over, which is a little island. Starting from the actual Pangea, around 250 million years ago, it started to rift. Okay, so starting from supercontinent status, which is the beginning of the Wilson cycle, the first thing that's going to start changing it is a rift that will literally pull the land masses apart. Okay, we've talked about a lot of parts of this for a while. This is what started the Mid-Atlantic Ridge. So you had the eastern and western hemisphere starting to split, go side to side, pretty much at the prime meridian. And then eventually ocean water filled that void. So it came from Panthalassa, that huge, huge sea that kept the planet a lot warmer. And it flooded in between. Okay, so that's step one, starting from supercontinent status, because we're eventually going to make a new one, given enough time. The second part, as your plates spread apart, once the ocean water has filled in that void, filled in that crevasse or that ravine or that rift, the sea floor spreading, so you have the split, the magma comes up and it forms new crust, and then it splits, and then the magma comes up and it forms more crust. This causes sediment to gather on the ocean floor. Now, this is the beginning of your oceanic crust, because we're starting off with continental crust that breaks apart. Eventually, these plates, as they're being moved apart, they start colliding with each other, and we have some type of converging boundary. You have different types of converging boundaries, but I'm not going to go back in depth, but we're specifically looking at an oceanic continental convergence at this point. This causes subduction. Okay, tomorrow is when we do continental. That causes what's called orogeny, which is mountain building. Right now we're focusing on the earlier stage. The oceanic subducts underneath the continental, and this is where we have lots of volcanic activity, because that oceanic is diving deeper down into the mantle and allows that magma to come up. We will talk more about volcanoes in the Ring of Fire. I want to say that is Tuesday, where I have volcanoes slated. But we have mentioned this stuff before. This should not be completely brand new. Terrain accretion. I did not misspell this. I know normally we spell terrain T-E-R-R-A-I-N. But this is the way it's spelled here. You have subducting oceanic, and it's carrying basically a little bit of continental on its back, like a turtle shell. And as the oceanic starts to subduct, because the oceanic is more dense because it's basaltic, that lighter continental crust that's forming on its back sort of gets like spot welded onto that continental crust that it's trying to go under. It's like it scrapes it off of its back. So I know some of you have done welding. You understand what a weld is. You attach one piece of metal to another. This is the same concept, but it's not metal. It's land that's being scraped off and being sort of super glued onto the whatever the shelf is that it's starting to go underneath. Orogeny is the fancy word for mountain formation. This is what happens when you have plates. Most impressively, when it's two continental plates, which are your big mountain ranges, that collide, and then the crust builds. The major difference between continental, and oceanic continental, both of them cause orogeny. Both of them cause the land to move up. But continental, they don't subduct. And since one of them can't go below the other, that's what causes them to go up, which is normally a folded mountain, which are the largest mountain chains. Like I said, we're going to go into mountain formation tomorrow. Eventually, Pangea did this. It's eventually going to move everything around the globe to the other side. And eventually, given enough time, we're going to have another massive supercontinent. It may not be 100% welded together, just like Pangea had that little island that was sort of stuck off on the side. You could see how the plates were still attached underneath the water, but you had that large island that eventually turned into North and South China that just didn't land-wise attach to the rest of that supercontinent. Given enough time, that supercontinent is going to do what Pangea did. You have erosion and you have rifting, and we start the cycle all over again. And Africa is still rifting on the eastern, if I'm not mistaken, it's the eastern part of Africa that is having another, almost like a mid-Atlantic bridge that's trying to happen again. It just won't be in the Atlantic. We've mentioned this before. Plate tectonics is probably the most important part of controlling the climate of this planet. It controls where the land is. It controls where the water is. Those two things control where sun radiation is either being held in, which is more water, because that has less albedo feedback, or if it's more reflective. Land reflects it back into space. If it's covered in ice or snow, that reflects it even better. In general, continental plates are older than oceanic. Oceanic is constantly being thrown back into the earth, is being remelted, is warming, is being brought back up, is becoming new oceanic, is hitting a new continental plate, is being forced back down. Oceanic is constantly being recycled by the earth, which is why it's younger. We have major formations on continents. In the order from oldest to youngest, oh, you know what? Really, the folded should be before basins. Shields are the oldest formation. This is sort of the center or the core of your continent. The oldest part would be the archaea, the bacteria. You guys do have an image that you're going to see in your canvas that shows it. I don't know how well you can see it because I had to shrink the picture down. Stable platforms are shields that have had sediment that has formed on them. And so they're sort of on the fringes of the shield. Where you have continental come together, we have orogenic belts or folded mountains. Not all mountains are folded, but that's the biggest ones. And then going out towards sea, we have what are called basins. Okay. Now, I've changed some of the wording a little bit here just to show you the more scientific and then the more generic. You should not be, oh, no. Put those away. Shields are the oldest. They are, because I don't want you guys, as you're eating, spraying your sputum into the air. I don't want to breathe your mouth particles. Shields tend to be the oldest. They are Precambrian, or the Archaea era. They are primarily metamorphic and igneous. Y'all, the oldest rocks were igneous at the beginning of the cycle. So it does make sense that the oldest continental formations are primarily metamorphic and igneous, less sedimentary. A platform is going to be sort of ringing around the outside of your shield. It's basically a shield that has had sediment on top of it. A shield and a platform is called a craton. It's a combination of the two. And like I said, I have an image that shows the different types of continental formations across the planet. It is color-coded in Canvas. I do not know if you can make that picture larger or not. You can always just Google it and find the image, and you can blow it up that way if you want to. Orogenic belts, this is the fancier term. This is a mountain formation. That's what orogeny means, is mountains. They are normally along the edges of continents for multiple reasons. We have one on the western coast, and we have one on the eastern coast. The Himalayas are between the Eurasian plate and then an Indian plate that came up and slammed into it. going much faster than most of the other plates were moving. And no, I do not know the speed of it. I meant to look it up yesterday and I just didn't do it. Not that they can tell like down to like a fraction of a centimeter how quick they're going, but I'm sure it's there. I just didn't look it up. A passive margin, which also can be called a basin, is going to be out towards your coasts. The least amount of geological activity is going to happen at a passive margin. Passive, not aggressive, passive margin. Basins do not have to be below sea level. These would be your lower lying plains. You can find them all over continents. They don't have to be at the edges, but basins do spread out, sort of like the, what is it called? When you go out on the ocean, so the seafloor before it drops off the continental shelf, that is considered a basin. I'm not saying that there's no geological activity ever there, but as the least common place that you would find it. This image is in your canvas. Okay, so our shields in the United States, so the top of it, so here's the Great Lakes. So that basically the United States cuts off about here. We don't have a lot of shield on our country. We have what are called stable platforms. We've got, this is an orogeny, this is your Rocky Mountains, this is an orogeny, this is the Appalachian Mountains. We have extended crust, which is essentially a basin. You don't have a lot of geological activity around the Gulf Coast. Unfortunately, they have hurricanes like really bad last year. But that's our country doesn't really have, except this itty bitty part up here by like, what is that? Montana or Wisconsin? I don't know all my states. I'm sorry if I'm from there and I don't remember. But that's really the only part that we have a shield that has spread down into our country. Most of the other countries have large portions of shield. And if you notice, Africa is basically a ginormous shield. You know, Africa, that's where apparently the first crusts were forming billions of years ago. The oldest land is found there. And you should have that in canvas because I'm not going to ask you to draw anything like that right now. I'm not asking you to learn any of the specific names of the plates or of the shields. I know that would change as the years go on. Did I leave something off of here? Where are you at? Above that image? Which part are you asking? Because I know I went through that part. Like I said, the oldest are the shields.
Says we could go on with not.
No, shields are continental landforms. There's only one of those that I did not mention in that previous section. Tectonic ages are, you know what, I need to take attendance. There's one more. Yes, let me freeze this and let me take online attendance because I only saw one person when I started. Tectonic ages, it's just that time period of when land-specific continental accretion is occurring for us. We're at the tail end of the Mesozoic, Cenozoic, so Mesocenozoic age. And the Cenozoic, or no, so wait. The Cenozoic, so the dinosaur age, that's when our western part of our country started coming up. That's at the end of the Mesozoic into the Cenozoic. That's about 90 million years ago, and that's when we started getting the Rocky Mountains coming up. Oh yeah, a lot of people online. Let's see. Chase Colton. Chase. Just a second. Esai. Keep in mind, if you miss that test Friday, you got an email from me. If you do not take care of that test by 9 o'clock this evening, it will stay a zero. I've extended it twice. Okay. Oh, Taylor. Raylan, Chase, Colton, Eastman, Joseph, Natalie, Sarah, and Taylor. Okay. So our Rockies, they started forming when dinosaurs were running around. Most of the western part of our country was a shallow inland sea. I've mentioned this before. That's why most of our bedrock is not granite, and it is made of limestone. Limestone forms in shallow waters. We're different. Most continents, most countries, for that matter, have a big shield area. We just don't. We have stable platforms, which are caused by shallow seas, and platforms are related to shields, but it's not a pure shield. The Rockies started forming about 80 million years ago. Okay, they ended a little bit more than 50 million years ago. So it took about 30 million years, really 25 if I subtract these right, to form the Rocky Mountains, which helped to build up the western part of the United States. So you've got California, Washington, Oregon, what else is over there? The Rockies and everything west, parts of Colorado, Nevada, all those areas. The Appalachians, they started to form almost 500 million years ago when the Euro-American plate started slamming into the Gondwanan plate or Gondwana land. All of those are acceptable for the southern part of our planet. And they ended about 300 million years ago. Now there are sections of the Appalachians that are billions of years old. So something else was going on besides this. This was pre-formation of Pangea. There have been other formations before Pangea. That's just where we like to start from. This was called the Allegheny orogeny. And y'all probably don't care because you probably have never visited Pennsylvania, but that's where I grew up. And one of the rivers is the Allegheny River. And I went, oh, those two things correlate with each other. I wonder if the Susquehanna has anything to do with that too. I didn't look. That's the other major river that's up in the Northeast. But Appalachians are much, much, much older than the Rockies. And like I said in the beginning, they're not as high. They've had more time to erode. Erosion and weathering breaks down and moves away the rock. Now, how tall were the Appalachians when they were formed? That I do not know. I did not look that up at all. But in general, a taller range is younger. Now, there are different types of mountains. We'll get into that tomorrow. The oldest mountain range, and this is one that was not on paper, I added this. The oldest mountain, the oldest rocks, the oldest mountain range that we found is 3.5 billion years old. Most of the oldest mountain ranges or chains or mountains in general do exist in Africa. Apparently, that is where the land started really forming billions and billions of years ago. And these would be almost completely igneous rocks. Yes, you're going to have some sedimentary on the top because of erosion, but if you get down into the rock itself, which is not loose, the true rock, the true earth, it should all be igneous in these older mountain chains. I don't know how to pronounce that. Macconjua? I have no idea how to pronounce that. I'd have to put it into the internet and tell it to pronounce it for me. No. I don't know, maybe. I'll have to throw that into Google and let it pronounce it for me and double check it. The Rockies are the younger ones here. The younger, we're going newer with plate collisions. The Andes are younger than the Rockies, but the Himalayas are the youngest mountain range, and they started forming about 40 million years ago. That doesn't mean that's when they ended. But of the major mountain chains or ranges, the Himalayas are the youngest. I'm not going over every single type of mountain range. But these are your oldest. This is the youngest in our country, and then just getting younger and younger. But yes, Everest, which is the tallest mountain in the world, is in the Himalayas. This shows you time periods when things formed. The oldest are the Archean. The couple slides ago, I showed you where our shield was. If you notice, that shield dipped down to about here, next to the Great Lakes. Well, that's the oldest part. The ones that are sort of like that purplish blue, those are your Precambrian or Archean. Our youngest crust is going to be this sort of orangish color. That's the one that formed the western part of the United States and lifted the Rockies. Most countries do have some older. Africa's got all different kinds of spots that are older around it. This just sort of puts it into perspective which parts of the continents actually formed first, which areas formed first and which ones formed the last. Stable platforms. We have a bunch of them because our country on the west coast was primarily a gigantic inland shallow sea. That is what a stable platform is. It was a basin that was filled with water. Our platform, once again, is made of limestone, at least the western part. So the eastern part, especially the northeast, no, it's granite, it's igneous, it's older. And this shows you the entire country over here itself. No, you're not going to have to like identify the parts off of the images on a test. I haven't built your test yet, but I'm not going to ask you to do that. Continents have two major processes in which they accrete or grow or get bigger. They're not the original formation, but how the outside, basically the continent grows from the inside out. You could have an uplift from the center of the earth, the magmatic differentiation. This happens multiple ways. It could be a hot spot, like out in Hawaii. If it normally, our volcanic activity is at a subduction zone where oceanic is going underneath continental. It could be just continental accretion. So you have magma, it's literally coming up from inside the earth and it's forming. It's spraying out as lava and it's forming on the surface of the planet. Continental accretion, however, when you have subduction, this is when you have, like I said, almost like the shell of a turtle on its back, riding on that oceanic crust. And when it starts going underneath that continental that's more stable, more stationary, it scrapes the continental from the oceanic off and it welds or it sticks it to the edge. These are commonly called island arcs. They're volcanic at subduction zones that are off the coast. And as it keeps subducting, it brings it along its back, just like eventually Hawaii is going to slam into whatever direction it's going, because Hawaii is heading west. That island chain will eventually be attached to, let's see, Hawaii is there somewhere around, give or take, Japan or China is what it looks like on here. If it heads straight west, Hawaii itself, the islands, they're moving. The hotspot's not moving. The islands are moving across the hotspot. And when it moves far enough past it, that hotspot's going to create a new island, but the whole island chain is still moving generally west. That is this continental accretion. So it is always, well, on the edges of the continents, is associated with subduction. We've already mentioned that ocean crust is constantly recycled and then forms back again. But that lighter, if it does have volcanic activity that reaches the surface, punches through the water, that's the part that it creates along the continental margin. This really says the same thing, just a different way. It literally gets scraped off the back of that oceanic plate. And like I said, it's just like what Hawaii is going to do. Wherever it ends up merging, over towards Japan and China, or unless something else comes up in its way, then it's going to accrete there. But your island arcs or your island chains normally get deposited somewhere on a more stationary continental plate. All right, here comes some weird words. I told my second period, it's almost like I'm trying to speak Klingon. An allochthon. Allochthons move from where they're formed. They are wandering rocks. Sometimes they move very far distances. I wish I could change this into like normal English, but unfortunately, this is the language of the geology here. We will talk more about different types of mountain folding or thrust. We've got fault block mountains, we've got folded mountains, we've got dome mountains, we've got volcanic mountains. Those are all words that we'll be learning tomorrow. But if your rock is a wanderer, if it moves, it's an allochthon. If it doesn't move, if it's formed, but it stays where it formed, like a shield does, then that's an autochthon. It's native. It has not moved around. Now we have some that move just a little bit, like they're really close to their origin, so the type of rock is the same from where it got transplanted to, and that's a parautochthon. Parautochthon. I can say that easy. Sort of like a hybrid between the two. So allochthon, autochthon, and parautochthon. Yes, I know. I'm sorry, but that's how they're pronounced and that's how they're spelled. Yes, I did look at the pronunciation because I wanted to make sure I was saying it the right way. The allos move, the autos do not, and the paras move just a little bit from where they formed from. But the general chemistry of the rock is the same. Two major ways that continents are changed. I've mentioned this word a couple times. Orogeny is the mountains are being formed. They weren't there originally, but your continental plates have slammed into each other and they have built up a mountain. Now, the biggest mountains are folded. We also have fault blocks. We have magmatic, which is volcanic, and we have metamorphic. Orogeny. It's an ah, not an is sound. This is literally, it's coming straight up out of the ground. It doesn't have faults. It's not folded. It's not crumbled. It's like a big flat plate that literally lifts up, directly up out of the earth. Oh, there's pictures. Pretty sure I put these on the image too. And I wanted to see if I could find a video that showed this, and I ran out of time this morning because I was running around talking to people. So the earthquakes and the folding and the volcanic, the big geologic like craziness going on, that's orogeny. The more stable version of this, where it's just coming straight up out of the earth, that's eporogeny. This is an image of how this works. So we had this oceanic plate, and we had some type of volcanic activity that was trying to form. It was creating less dense material that literally is sandwiching itself up against the continental crust that is more stationary. This is very, very similar to a lot of the images that we've seen. This is showing how there's different kinds of a thrust fault. We'll talk about the language of this. If it goes down, it's called a certain thing. If it goes up, it's got a different name. But this is all a lead-in to what we are doing tomorrow, specifically with the mountain formation mode. So it should be shorter like these. And we still have over 15 minutes left in here. I need to get into my grade book. Let me stop this.